Hi everyone. Today I'll be discussing this paper called On the Expressivity of Markov Reward. So, it is a reinforcement learning paper, and it also got the Best Paper Award from NeurIPS 20, the Outstanding Paper Award from NeurIPS 2021. So, that's why it caught my eye. And it is from folks from DeepMind, Princeton, and Brown University. So, it is a pretty theoretical paper. I mean, there are a lot of thought experiments in it, and uh, uh, authors present some theory and they give proofs of it and explain it. So I'm just an undergrad right now, and I don't really have the necessary theoretical background to deeply understand all this and to actually do justice to the paper. But I'll try my best to explain whatever I was able to understand, and so it might help someone who is also struggling to understand such theoretical papers. So yeah, let's begin. So the main premise of the paper is like tackling the reward hypothesis of reinforcement learning. So the reward hypothesis states that for any desired behavior, task, or other characteristic of agency, there must exist a reward signal that can incentivize an agent to learn to realize his desires. Basically, if you have any task that you want an agent to run, you can express that task in a form of a reward signal, and if the agent tries to maximize that reward signal, it will essentially solve that task. So this is called the reward hypothesis in reinforcement learning, and it is one of the fundamental assumptions of reinforcement learning. And this paper is tackling that fundamental hypothesis, and it is doing a systematic study of the reward hypothesis by trying to understand the expressivity of a reward as a way to capture tasks that we would want an agent to perform. So they want to actually understand that how expressive a reward really is. Is it really true that you can use a reward to express any task? And they also tackle the question like, what does even a task actually mean? So yeah. So so first they introduce three notions of a task. So they work on three notions of a task. First is a task could be a set of acceptable behaviors. Here, behavior is basically a policy of an agent. So, a task could be a set of acceptable policies, or it could be a partial ordering over policies, or even it could be a partial ordering over trajectories. So, I'll go into detail about what all these three tasks mean later on. So, but yeah, they give this three notions of what a task might mean. Now, based on these notions of what a task might mean, they investigate that and they prove that while a report can express many of these tasks, there do exist instances of such tasks that no Markov reward function can capture. So there exist tasks which for which you can't express them using a Markov reward. And then so this directly tackles the reward hypothesis, which says that uh, a reward can express any task you want. And then they provide a set of polynomial time algorithms that can construct a Markov reward function. So basically, it says that if there exists a reward for that, if there exists a reward that can express that task, these algorithms would find that reward in polynomial time. And if no such reward function exists, the algorithm would tell that in polynomial time that, okay, no such reward exists for this particular task. So that's the basic premise of this paper. And yeah, let's go into detail. Okay, but before going into the paper, let's discuss this section that they have, which basically summarizes what other perspectives people have had on reward. So it was pretty interesting. So I thought we should cover that. So one thing was this two roles of reward. So uh, reward can both define the task that the agent learns to solve and also define the breadcrumbs that allow agents to efficiently learn to solve the task. So what they mean is that a reward can both specify the task, like uh, if we want to go to a maze, to the end of the maze, the reward can specify the task that our task is actually to go to the end of the maze. However, the reward can also specify how to efficiently learn to solve the task. It can provide sort of breadcrumbs for that. So I think what they mean is that if you have this maze, the reward can specify that okay, this is the place which has the highest, which has the potential for highest reward. So you need to go there. So it specifies the task. But if you also reward the agent in the middle, in between, so it can sort of give you a pathway or it can tell the agent how to learn to actually solve this task. So if we apply approaches like uh, value iteration or TD learning or stuff, the agent will use this final reward to learn value functions for each of the intermediate states, like to learn okay how valuable this state is, how valuable this state is, how valuable this state is, and this will all be learned by the reward. And so this would give it sort of a pathway to how to actually learn to solve this task. So these are two roles of a reward. It can also define the task that you want to solve, and it can also give you a way to solve that, to learn how to solve that task. Then there are preferences. So what it says is that instead of just having numerical scalar rewards that like you got a reward of plus 10 or you got a reward of plus 20, preferences can be a sort of reward in themselves. So you can tell your agent, you can give signals to your agent based on what is your preference over a state of actions or trajectories. So like if I have a maze here and there is a dead state here where you will die. So you can say to the agent, okay, that this trajectory is good and this trajectory is bad. So you can express the reward. You can use a reward as a preference over trajectory that okay, this trajectory is better than that trajectory. Right. So reward can also be in a way of a preference. Then you can also uh, learn a reward from behavior. So in inverse reinforcement learning, what the thing is that you have a human demonstrator. So basically, you have a human solving a task. So maybe I want to learn how to lift my. Maybe I want to teach an agent how to lift a bottle. So you'll have an you will have the agent watch demonstrations of a human lifting the bottle, and you will show him it multiple demonstrations how a teacher agent tries to lift the bottle. And the idea there is that from those demonstrations the agent can somehow infer what the teacher actually wants to do, and it can infer a reward function out of it. So by repeatedly seeing me lift the water bottle, it can create a reward function that rewards lifting, that reward behaviors that lead to lifting the water bottle. So in that sense, rewards can be learned, right? And also reward misspecification. So rewards are notoriously hard to specify. So the thing is that you might think that your reward function works. You might design your reward function to work in a particular way, but because you have misspecified the reward somehow, the agent will sort of game the reward to to get the maximum reward. It will if you train an agent, then it will obviously try to maximize the reward. But it is possible that maximizing the reward is not what you actually wanted. So when you wanted to maximize the reward, but the way you designed the reward, it didn't account with how you wanted to actually solve the task. So there's this nice blog called faulty reward functions in the wild by OpenAI. And they have this example of this post runner environment. It is a pretty standard example where the actual task is to solve the race as fast as possible, but the agent is actually rewarded for hitting this green targets. So what the agent learns is that it keeps on going in circles and circles to hit these green targets, which keep on respawning, and it doesn't actually reach the goal, and it doesn't perform the tasks that the humans actually wanted it to solve, but it instead tries to maximize the reward. So here the problem was that the reward was sort of in a way that, okay, if you keep on hitting these green targets over the way, you would eventually reach the goal as fast as possible. But this was a case of reward misspecification. So the agent instead tried to find this hack to maximize its reward. Right. So yeah, so rewards are also terribly hard to specify, as can be seen here. Also, it is important to understand that the framework that they have proposed in this paper has a lot of assumptions embedded into it, and the authors really admit that, okay, they are considering the space a bit so that they can develop a framework for it right now, and the relaxations of those constraints are a critical direction for future work. So one is that the reward functions are Markov and deterministic. Deterministic means that it is deterministic. There is no probability or stochasticity associated with it. With the same settings, you will get the same reward every time. The fact that they're Markov means that it does not depend on the history. The reward does not depend on the history of your states or whatever it was. It just depends on the current state and or the previous state action. Yeah, this the current state and the previous state. Uh, and second is that the policies of interest are deterministic. So they're not dealing with stochastic policies right now. So the agent's behavior is deterministic. The environment is a finite CMP. Finite means that it has a finite number of states. CMP is a controlled Markov process, which is basically a MDP, Markov decision process, without any reward. Just remove the reward out of it. Uh, Gamma is because we are designing the reward ourselves. And gamma is a part of the environment. So they're assuming that gamma is not set by us. Gamma is the discount factor, which basically says how much we value states in the future less, and that is a part of the environment. They also ignore the rewards role in shaping the learning process. So if we go back to the two roles of reward, the first role was to define the task, and the second one was to guide the learning process. So they're ignoring the rewards role in shaping the learning process right now. And sixth is that they are currently just comparing different states or different policies or whatever based on the value or the return obtained from the start state. So if you have an MDP, they're just comparing approaches based on what the value of the return is from the start state. So that is what they're using as a proxy to determine if a reward function realizes a given task. All right, so these are some pretty major assumptions that they make right now. But it was good to see that, okay, they are clarifying that, okay, we are considering the problem a lot right now to make it feasible to develop a theory out of it. In future work, they will relax. They say that, okay, in future work, someone could relax his assumptions and make this theory go ahead. Right, so that was nice. Okay, so let's dive deep into the main part of the paper. So we have two agents or whatever, Alice and Bob. So Alice is basically a designer who's designing a task, and Bob is an agent who's trying to learn how to solve that task. So basically, Alice has a task in mind, which is in some task space, and then Alice has to somehow construct a reward function to incentivize Bob to pursue this task. All right. So they divide this thing into two stages. The first is the task definition question, task Q, in which Alice thinks of a task that she would like Bob to learn to solve. And the second is task expression question, expression Q, in which Alice creates a reward function and perhaps uses the gamma that conveys the task to Bob. I would say that is a reward might be an answer to the question of expression queue, the task expression question, instead of the task queue or the task definition question. So reward can be treated as an expressive language for incentivizing reward maximizing ends. So basically can Alice is doing the task definition question in which she thinks about okay what the task is. She has a lot of knowledge about the task. So in fact she might know every detail of the environment and define the task based on whatever extra knowledge she has about the environment. And Bob must learn how to solve the task through the interaction based on the reward only. So Bob's capacity is relatively limited compared to that of Alice. So, so under this view, we can assess the expressivity of reward as an answer to the expression queue conditioned on how we answer the task queue. So say if task queue is expressed in terms of a natural language description, so if Alice is thinking about the task in a sense of a natural language, okay, so move this box from this place to other place. That is the task queue thing. Alice is thinking about how to frame the task, of like or what the task is. So the space of that might be natural language. So Alice might be thinking in terms of natural language to move this thing from one place to another. And the expression queue would be defining a reward to actually teach Bob how to do that. So this is very difficult because you have to because there is a mismatch between the abstraction of what a thing in natural language means, like moving box from one place to another, and what a reward can convey. So a reward could be a scalar reward, or as they will propose three different types of how a task would be. A reward is a reward is still very under constraint solve this to solve a lot of task spaces, like a task spaces which are expressed in terms of natural language. So yeah. So let's answer the first question of task queue, like what is actually a task? So you can think that a task might be defined by the optimal policy. Like what is the behavior that will lead to solving the task as fast as possible or as quick as possible. So if you have a maze, the task might be defined by the behavior which allows you to reach the goal state as fast as possible. So if this is the goal state, they're saying that okay, the task is to reach the goal state as fast as possible. The problem with this approach is that it fails to distinguish between the non-optimal behaviors. So because if there is a fire, and this is the optimal approach. But what about the non-optimal approach? So how would we distinguish between an approach which just goes here to an approach that goes into a destructive state? So yeah, so just specifying the task in terms of the optimal policy is limited because it does not distinguish between the non-optimal behaviors. So what they say is that okay, we should have some flexibility in our task in the specification of tasks so that uh, we can we can basically scale from specifying only the optimal behaviors or the desirable behaviors to even an arbitrary ordering of the behaviors. So we should be able to even order the behaviors if we want to. So for this, they propose three answers to the question of task queue, which they think are general enough. The first is a set of acceptable policies. The second is a partial ordering over policies. And the third is a partial ordering over trajectories. They say that they adopt these three because they think that it can capture many kinds of tasks while also giving a lot of flexibility to the amount of specification you can put in there. Okay, so let's discuss the set of acceptable policies first. So it is a generalization of the task as pi star or task as optimal policy. So it is a generalization of the definition where you define a task as the set of optimal policies. Right. So instead of set of optimal policies, it is you're saying that okay, these are the set of acceptable policies. Right. So you defined a task as a set of acceptable policies, which is a non-empty subset of the deterministic policies from all the set of possible deterministic policies. So basically, you are saying, okay, these subset of policies are acceptable, and that defines the task. Now, uh, now once you have defined a task, we want to understand what it means for a reward function to properly realize, express, or capture that task. So what they say that a reward function is set to realize a task if the start state value or return induced by the reward function exactly adheres to the constant of the task. So basically, they're saying that if you have a task and it has some constraints, then the reward function should be in such a way that the value of the starting state should respect those constraints, should exactly represent those constraints. So for the set of acceptable policies thing, so the way we realize a task is that uh, for a given environment E and a set of acceptable policies by G and a reward function R is set to realize the set of acceptable policies if and only if the start state value function is optimal for all good policies and it is strictly higher than the start state value of all other policies. So basically, what this says is that the value induced by the policies which are in the uh, set of acceptable policies should all be equal, should all be optimal, and they should be greater. They should be strictly greater than the start state value induced by all other policies. So this is basically a generalization of the task as pi star thing. So one way this could be realized is that what I just said that okay, uh, all the policies in PyG have optimal start state value and all other policies are suboptimal. So this is called equal SOAP or just SOAP. But there is another way in which we might only require that the acceptable policies are each nearly optimal, but they are allowed to differ in the state value somewhat for some epsilon, as long as they are better than every other bad policy. So basically, you have a bunch of acceptable policies which are nearly optimal. So the value induced by them should by each of them should differ by each other by at max epsilon. So they are in an epsilon range of each other, and they're optimal, and their value is strictly better than all the other bad policies. So this is called range SOAP, and this is a more general version. And if you set epsilon equal to 0, and we basically say that all optimal policies, all acceptable policies should have the same exact value, then you get equal SOAP. But range SOAP is a more general version. And what they say is that there exist range SOAPs that are expressible by Markov rewards that are not realizable as an equal SOAP. So every equal SOAP can be expressed as a range SOAP, but every range SOAP cannot be expressed as an equal SOAP. So here is one such scenario where you can express it as a range SOAP, but you cannot express it as an equal SOAP. So you have these two states, S0, S1. Taking action 1 or 2 takes you to the other state in both of them. All right. So if you express the SOAP as pi 1 1, 1 2, and 2 1, pi 1 1 basically means you are taking pi 1 2 basically means that you are taking 1 in S0 and 2 in S1. So if you define the SOAP as pi 1 1, pi 1 2, and pi 2 1, the only policy that is remaining is pi 2 2, and it is a bad policy by definition because it is not in the subset of the, it is not in the set of the SOAP policies. Now, in equal SOAP, what you would want is that you would want all these three policies to be optimal, to be exactly equal and to be exactly optimal. What this is that any reward function which will make these three policies optimal, exactly equal and optimal, will also make PO&TO, which is the only bad policy, optimal. Basically, you can say that, okay, if, okay, let me insert some text here. Yeah. So let's denote uh, taking the first action in state 0 by x naught. Basically, the reward you get by taking the first action in the first state as x naught. All right. And the reward of taking the second action y naught and similarly x1 y1. So in pi11 you will get x naught plus x1. This is the reward you get from pi11. And what they're saying is if you equate it to pi12, what you're doing is that it is x naught plus y1. And that is also equal to y1 is basically taking the second action in the second state. And that is equal to y naught plus x 1. Yeah. So these are the three equations. Here x naught is here x is the first action and y is the second action, and naught represents the first state and 1 represents the second state. From this you can get that okay, x1 equal to y1 and y naught equal to x naught. So what will be the reward of the PO&TO? It would be uh, y1 plus y naught plus y1, right? And from x naught plus x1 equal to y naught plus y1 x1, you can get that x naught equal to y naught. So you can replace this y naught by x naught, and you will get x naught plus this would be converted to x naught plus y1, and you will get exactly this. So basically, if you do this, you will make the only bad policy which remains PO&TO optimal as well, and that would negate the condition that the value of the policies in the optimal set in this S SOAP should be strictly greater than the bad policies. So this happens when you do equal SOAP, where you say that okay, all the all the policies in the SOAP set should have the exactly same optimal policy. Now, if you do the same thing in a range SOAP, in which you can assign lower rewards to A2 than A1 in both states. So basically, taking the second action has a lower reward than taking a first action. So pi11 will have the maximum reward, and pi22 will have the minimum reward. So there would be sort of an ordering. So pi11 will have the maximum reward. Pi12 and pi21 will have equal rewards, but those equal rewards, I mean, they could have equal rewards or they could be different. And probably they'll have equal rewards. And but the, and pi22 will have the least rewards because it takes two of the A2 actions which have a lower reward than the A1 action. So pi22 will have the lowest reward, pi11 will have the maximum reward, and pi12 and pi21 will have rewards in the middle. So because it is a range SOAP, you can have so the policies in SOAPs which differ from each other by some epsilon. So it is not a strict requirement that okay, pi11's reward and pi12's reward should be equal. They can differ by some epsilon, but they should be greater than the bad policy pi22, which is the case in this range SOAP. So here this is the case where you can express this by a range SOAP, but you cannot express this by an equal SOAP. So the next way of defining the task was a partial ordering on policies. So Alice can choose a partial ordering that, okay, she can say that some policies are great, some are good, and some are bad policies to strictly avoid, and she can remain indifferent to the rest. I think it is a part, that's why they're calling it a partial ordering. Maybe. I'm not sure why it is a partial order. Maybe they don't have to order all of them, but I'm not sure about that. So partial ordering strictly generalize equal SOAPs because an equal SOAP is basically a partial order with two equivalence class. So in equal SOAP, you have a set of acceptable policies and bad policies. So you have a partial ordering with two classes. So partial ordering is a generalization of equal SOAPs. So they say that a reward function R realizes this part- realizes this task definition L pi. Basically, L pi is the partial order. If and only if in the resulting MDP, the start state value function that orders pi according to L pi. So basically, the reward function realizes the task if the partial ordering of the uh, starting state value of different uh, policies is in the same order as the partial order that was defined in the task definition. So basically, the reward should order the policies in the same way that the task told it to order. In that case, you can say that the reward has realized that partial ordering. Total or TO or partial ordering on trajectories is a step ahead of this. Basically, instead of just a policy, you specify a partial ordering on a on trajectories or on length in trajectories of SA pairs. So basically, it is you just order trajectories. A trajectory is a sequence of state action pairs that the agent encountered, and you say that okay, this trajectory is better than that trajectory, and the reward realizes that if basically the discounted rewards across those trajectory obeys the same partial order as that was defined in the original partial order. So basically, in both partial ordering on trajectories and partial ordering on policies, the main thing is that the reward should induce the same partial ordering that was defined in the task. Okay, so now let's talk about the expressivity of the Markov reward. So they process this theorem, they propose this theorem. What they basically say is that for each of SOAP, PO, or TO, there exists environments and tasks defined in that environment for which no Markov reward function realizes that task. So basically, there exist tasks in certain environments for which there is no Markov reward which can specify that task captured properly. So okay, so what are such tasks really? So intuitively, what this is that such tasks would involve policies or trajectories that are correlated in value in an MDP. So basically, if two policies are nearly identical in behavior, it is unlikely that reward can capture the partial ordering that places them at opposite ends of the ordering. So if there are two policies which are nearly identical, I mean they're nearly identical, there couldn't be a partial ordering or a reward which has a partial ordering in which both of them are on the opposite side of the ordering, right? But we can actually ask for such a task, right? The task definition is in our hand, so we can actually ask for such a task, or it won't be possible for a reward function to express that. So a simple example of that is to always move in the same direction task in a grid world. So basically, you have a grid world, and the SOAP here is the policies which move in the same direction, like the one which always moves to the left or up or right or down. So if we have a SOAP in which consists of the policies which moves in the same direction every time, right? So essentially, this will make all of the policies have the same value because you're saying that at every grid, moving towards the left is optimal, moving towards the up top is optimal, moving towards the right is optimal, and moving towards the down direction is optimal. So essentially, any policy is optimal in this case. But if we restrict the SOAP to only consist of policies which always move towards the left, always move towards the top, then in such a case, a Markov reward function cannot realize this task because it will it is not you can't design a reward function which gives a higher value to these policies and not to any other policies, because if you have this grid And in this, you are saying that okay, moving to the top is optimal, moving towards the left is optimal, moving towards the right is optimal, moving towards down is optimal. So any arbitrary trajectory is also optimal. But this would actually be a bad trajectory because our soap only consists of trajectories which move in the same direction every time. But there is essentially, you can't define a reward function which gives, you can't define a Markov reward function which gives this a lower value and these policies a higher value. So this is one such case in which no Markov reward function realizes this task. Then they give example of this soap, and in this they take the soap as pi 2 1, basically taking 2 here and 1 here. If we consider this the soap, then both pi 2 1 and pi 2 2 will have the same value because this is the starting state, and both of them are taking the second action in the first state, right? So they are never actually reaching the this state. So we have pi 2 1 and pi 2 2, right? So they differ by the action they take in this state, but they're never reaching this state. So if we take the soap to only consist of this, we would want that this would have a higher value than pi 2 2, but you can't define a reward function which would give a higher value to pi 2 2 and which would give a higher value to pi 2 1 and a lower value to pi 2 2. So this is another case where a Markov reward cannot realize this task. Then we have this case in which they take the soap as pi 1 2 and pi 2 1. So basically the thing is that you have to take one action in one state and another action in one state. And if we make both pi 1 2 and pi 2 1 optimal, basically we are saying that taking the first action in this state is optimal when we are considering pi 1 2. And also when pi 2 1 is there, we are saying that taking action number 2 is also optimal in this state, right? And followed by this, also we are saying that okay, taking state action 2 is optimal here, and also taking action number 1 is optimal here. So basically all actions are again optimal in this. So in this also you can't define a reward function which makes the trajectories which are left, which are the bad policies, pi 1 1 and pi 2 2 suboptimal. They will also be optimal, right? So again, this is a case where Markov rewards cannot express a task properly. So yeah, overall here they basically gave some examples of tasks which break the reward hypothesis, where they say that okay, given any task, you can specify what the reward, you can specify a reward which expresses this task. So they are saying that okay, there exists task for which there is no Markov reward which can express that task. So yeah, that's pretty cool. Okay, so now they propose this reward design task, which is basically given a task, you need to figure out a reward function which ensures that the task is realized. Basically, the reward function realizes the task. So they propose algorithm, and they say that okay, that algorithm, if there exists a reward which can realize a task, the algorithm can find that in polynomial time. And if no such reward exists, the algorithm can figure that out in polynomial time, that okay, no such reward exists which can realize the task. So they don't detail the algorithm exactly, right? But what they give an intuition about it. So what they're saying is that these algorithms compute the discounted expected state visitation distribution for a collection of policies. In the case of SOAP, for instance, these policies include pi-g, which is the SOAP policies, and what they call the fringe. So the set of policies that differ from pi-g by exactly one action. Then we use these distributions to describe linear inequality constraints, ensuring that start state value of the good policies are better than those of fringe. So basically what they're saying is that, okay, if we have a SOAP and in that we have some policies, right? We have some policies, okay, so say we just have policy which moves upward always. So this is our SOAP, the policy which is our SOAP. Then they'll calculate fringe policies, right? Which just differ by one action. So maybe that policy goes like this and then it takes a right turn here. So this is the fringe policy, which is almost same as as a SOAP policy, but just differs at one action, at exactly one action. And then they organize this as a linear programming thing. And the constraints there are that the value induced by the policy that was in the SOAP should be strictly higher than the uh, value of value of the fringe policies. This is because the fringe policies are the ones which will probably have the nearest value as compared to the SOAP policies. So they are constraining that okay, these fringe policies should have lower value than the policies which are in the SOAP policies, and this is framed in a linear programming fashion with constraints and stuff. I don't exactly know much about linear programming, but yeah, that is how it works. And yeah, they compute the discounted expected state visitation distribution. Basically, I think they figure out what would be the probability that each state is uh, visited when you follow these policies. It is somewhat like finding the stationary distribution of a Markov chain. Here is the algorithm. They compute the fringe of the SOAP policies. Then for policies in the SOAP, they figure out the state visitation distributions. For the fringe also, they figure out the state visitation distributions. Then they add an equality constraint. Basically, if we consider the equal SOAP, we would want that the values induced by all of the policies in the SOAP should be equal. So this basically says that the value induced by all of the SOAP policies should be equal. And okay, this is a and this is the inequality constraint which says that okay, the values induced by the SOAP policies should be greater than the values induced by the fringe policies by some epsilon. And then they frame this as a linear programming objective in which they have to maximize epsilon. So they have to maximize this margin between the fringe policies and the optimal policies, constrained to the fact that we have these inequalities and equalities. And they solve this linear programming and get R out and epsilon out. Epsilon out is probably the margin between the fringe and the optimal policies, and R out is the reward function which we get. So if epsilon out is greater than 0, then we basically there's a separation between the values of the fringe and the optimal policies. Then there exists a reward, obviously, which can specify it. So we get that reward. And if epsilon is 0, so that we can't differentiate between policies which are in our SOAP set and outside of the SOAP set, then we return this thing, which basically says that okay, the algorithm found no such reward, and it returned that okay, no such reward can be designed. And they're saying that this algorithm works in polynomial time. Then they come to experiments. So in this, basically they show the amount of SOAPs which are expressible. So which are expressible by a reward. So the blue line shows the equal SOAPs and the gray line shows the range SOAPs, and this is a fraction of expressible SOAPs. So they have a lot. They have, say, I think hundreds of or whatever, 200 random SOAPs, right? So point two basically means that out of those 200 random SOAPs, only 20% of the SOAPs were expressible through a reward. So one thing that you can see here is that the gray line is above the green line. So this basically shows that the range SOAPs are more expressible than the equal SOAPs. That is one. And also there are various trends that can be interpreted of that how if we vary the number of actions, the number of SOAPs, expressible SOAPs vary. But they state themselves that okay, these trends are not that reliable because they also depend upon the SOAPs that they have particularly defined. So they are not general trend. But here they do say that okay, if the spread of pi g is more, so if pi g has a very high state space, then if you as the policies become more and more spread out, the number of realizable policies decreases and decreases, because the other says that if in a very spread out state space, there will exist corner cases which break, but there will exist more cases which will break the reward hypothesis, because as you see above, we could design some weird situations in which the reward hypothesis is broken, and if this policies become more and more spread out, there will be more and more such cases that are possible. And okay, in the second experiment, they show that using their SOAP, the reward function designed by their approach, allows the agent to learn way faster than the regular reward function. So if in this grid space you have a regular reward function which just gives a reward of +1 here and -1 here. So compared to this regular reward function, using the SOAP reward function, the reward function we get from the whole linear programming thing, allows you to learn very quickly. So yeah, that was all for the paper. I really like the setting of the paper, like how they targeted one of the fundamental hypotheses of RL, and I loved how they designed theoretical experiments, how they constructed counter examples and stuff. So it was a good read, and I think the paper was very well written, so that even an undergrad like me with not so much theoretical knowledge could understand it. The only critic, if any, I have of the paper is the constraints, like the constraints I mentioned before. Uh, I think the constraints are very restrictive, and it could be that the claim that it gave that okay, Markov rewards are not expressive enough. It might simply be due to the fact that they have constrained the problem a lot. They are taking Markov rewards and deterministic policies and all of that. So, but thing is that they have freely admitted that okay, they have constrained things a lot, and so really relaxing those constraints is a part of visual, so that is fair. Also, one quick thing was that they said that their approach works in polynomial time, but I'm not sure because they are computing the state with rotation distributions of the entire MDP, right? So uh, if the MDP state is continuous, if the state space is continuous somehow, this might be computationally intractable and it might not be actually polynomial in time. But that is again something that could be approximated using a neural network or something, probably, I guess. Yeah. Uh, I mean, I don't think it is even possible to do that in polynomial time in continuous spaces. So yeah, that is something that is obviously not possible in continuous spaces anyway. So and it would have to be done using approximation. So a good future work would be how this good future work might be how this holds up in using nonlinear approximators like neural networks and stuff. But yeah, it was a great paper and I had fun reading it. So yeah, that's all and thanks for listening.